6.2 Part 1. Today we're going to evaluate polynomial functions. Your essential question, what is a polynomial function and how can you use synthetic substitution or synthetic division, I'll use those interchangeably, and that's going to be new to you, to evaluate a polynomial function. Polynomial functions are not new to you. Okay, polynomial functions like linear functions are polynomial functions. Quadratic functions are polynomial functions. And there are many, many, many more. So today we're going to learn even more of them. And we're going to learn about what makes a function a polynomial function. Before I define a polynomial function for you, I'm going to give you a very complicated example. A function f of x. And I will do 10x to the 6th. 15x to the 5th, 7x to the 4th, minus 4x cubed, minus 2x squared, plus x, minus 7. There you go. I just made a really complicated function, a polynomial function. This has many, many terms and a high degree. Or I'm going to use that function to help me explain the definition of a polynomial function. So down here you can see the definition of a polynomial function, and they wrote it as f of x equals, and then you've got, for them, they've got 4 terms total. Now this first term, this is going to be your leading term, where this leading term has a coefficient a sub n. A sub n happens to be your leading coefficient. Because n is your highest degree, and the coefficient in the term with the highest degree is always your leading coefficient. And then at the far right here, we have our constant. A to the a sub 0 is your constant. Notice it has no variable next to it. So in my example above, my leading coefficient is 10 because it is in the leading term, and that term happens to have the highest degree. It has a degree of 6. This tells me a lot about this polynomial function. The other part of this that I can see is the constant. The constant is at the far right. It is negative 7, and that's going to tell me that the y-intercept is going to be negative 7 because our constant, if we plug 0 in for all the x's, our constant gives us our y-intercept. In between these terms, so my first term is a sub n x raised to the n power. My next term is a sub n minus 1. So if my first term was like the 6th degree term, then n minus 1 is my 5th degree term, right? So a sub n minus 1 in my example above would be 15, and x raised to the power n minus 1 would be my 1 less degree than my leading term, so that's going to be a 5. And then it's got a bunch of dots there. So the dot just represents all the terms in between before we get to our linear term, which is sub 1 and then x raised to the first power. So linear means just x to the first power. And then our constant term, which is sub 0 times x to the 0 power. X to the 0 power is just 1, so you don't even see the x there. So the terms in between could be written, for example, as like after a sub n minus 1, x raised to the n minus 1, you'd have a sub n minus 2 times x to the n minus 2. So think about that. Basically, that's going to be your 7x to the 4th term. Because n minus 2, if we take our degree of 6 and we minus 2, we get a degree of 4. Okay, and then going to our next term over, negative 4x cubed, well, that's our 3rd degree, and that is 3 less than 6. So that would have, the coefficient would be sub n minus 3, and then x raised to the n minus 3, and so on. So it's a complicated definition, or at least it looks complicated, but it's really not complicated if you just kind of compare what's happening and try and really understand what's going on. There are a few rules with this definition. The first rule is that all of your exponents have to be whole numbers. Okay, why is that? Well, x, like to the 1/2 power, that's really like the square root of x. And the square root of x is a function, not that you should know this right now, but it's a function that looks like this. This is not a polynomial function. It is not continuous for all x values. This is my x-axis. You also cannot have any variables in your denominator. All right, let me give you an explanation for that. So 1/x is not a polynomial function. We can also write this, now that we know about negative exponents, as x to the -1. So if you have negative exponents, remember that basically we have to take the reciprocal of that base, so you end up with a variable in the denominator. And this function, not that you'll know this right now, we call this a hyperbola. There's my x-axis, there's my y-axis. It's not a continuous function. It's not a polynomial function. Okay, another one is that there are no variables in the exponent. So for example, if I gave you like 2 to the x power, we actually call this, and you don't know this, well, you've learned this before, but I'm not expecting you to know this, but this is an exponential function. And an exponential function looks something like this and has a thing called an asymptote. And we'll get into that later, but not a polynomial function. And then, of course, our coefficients have to be real, because if they're imaginary, then we can't even graph these in the real coordinate plane. Okay, so those are some important rules to keep in mind when you are identifying whether or not a function is in fact a polynomial function. And we're going to learn about all these other functions over here that are not polynomial functions in the future, so don't worry about that. All right, terms. Well, hopefully you already are pretty familiar with this, but terms are the product of numbers. We usually call those numbers the coefficients, and variables. And in the function above, so my example, well, how many terms do we have? Well, the number of terms, let's see, we've got our first term here, right? A combination of a number, which is 10, and a variable, x to the 6th power. So there's 1 term, 2 terms, 3 terms, 4 terms, 5 terms, 6 terms, and 7 terms. The constant does have a variable. It just happens to be x to the 0 power. Okay, so x to the 0 power is just 1, so you don't even see it. So there are 7 in example above. All right, standard form. Hopefully you are super familiar with standard form. This just means that the terms are in descending order. Of powers. When you're working with polynomial functions, just like when you were working with lines and quadratics, you want to put them in standard form for many reasons. And like we saw in quadratics, it was important because if you wanted to factor them, or if you wanted to figure out your A, your B, and your C for your quadratic function or your quadratic formula, all of that was really important. Now, in our example above here, it's already in standard form. I wrote it like that for you, but if it wasn't, then you would just make sure to put it in order of descending powers. So we go from x to the 6th, to x to the 5th, x to the 4th, x to the 3rd. And again, that's where that n-1 in the definition comes from. Let's talk about different types of polynomial functions. So I've made a table here with different degrees of the polynomial functions. That's the first column. Second column, we're going to name the type of polynomial function. I've given you one example of that type of polynomial functions. There are many. And then the polynomial function in standard form. And so you should be really familiar with a couple of these. And I'm actually going to start with one that you're super familiar with. We're going to start with a degree of 1. So go down to the second row where it says degree of polynomial 1. The type of polynomial that you see graphed here is what we call a linear function or a linear polynomial. And in standard form, you're really used to seeing, well, the form that you're used to seeing is y equals mx plus b. You might also see this as ax plus by equals c. Okay, so those are just two forms, and even the parent graph of this, and I'll talk more about that later, but the parent graph of this would go through the origin, have a slope of 1, and so it would just be y equals x. So there you go. There's many forms of it. Standard form is truly the ax plus by equals c. All right, now let's use the slope-intercept form to go back to the first row and talk about a degree of polynomial 0. Okay, well, that is what we call a constant function, because no matter what input you put in, it's not affected. You always have the same output. So the output is constant. Okay, so this is going to be a constant function. It's basically a linear function that's just a horizontal line. And maybe we'll call this one, because there is no slope, right? The slope is 0. It looks like this in slope-intercept form. So really you could just call this y equals b, which is the y-intercept. Or how about we use y equals k, and k is some constant. Like in this example, maybe k is 2, right? So maybe in this one we say, okay, it's y equals 2. Going down to the third row here, this is a quadratic function. We just finished learning about these parabolas that have a vertex that we call a max or a min. And when you learned about this one in standard form, you learned it as ax squared plus bx plus c. We also learned about it in intercept form and in vertex form. And the most simple version of this would just be y equals x squared. Okay, but standard form, maybe I should highlight your standard forms, because I'm giving you so many examples. There's standard form, this is standard form, and this is standard form. All right, the rest of these polynomial functions, their standard form is going to follow the quadratic standard form. So the next one is what we call, it's degree 3, so it is cubic to the third power. And its standard form would look like this, y equals ax cubed plus bx squared plus cx plus d. The next one is what we call quartic. Fourth degree, think quarters, right? 4 quartic. And its standard form will be y equals ax to the 4th plus bx to the 3rd plus cx squared plus dx plus e. So you can see we just keep adding one more term, so we have to, our constant just keeps going up by one letter. And a 5th degree polynomial, we call that a quintic. And that is to the 5th degree. So now let's see, I'm probably going to run out of room. So let's try and start a little further over. We'll do y equals ax to the 5th plus bx to the 4th plus cx to the 3rd and dx squared and ex and f. So those are the standard forms, and whatever degree you have, you just keep adding more terms I've written these all in standard form, so they're all in descending order of power. Let's do an example. Example 1 is the function of polynomial. If so, write it in standard form, state the degree, type, and leading coefficient. Let's look at A. In order to determine if this is a polynomial function, we have to determine if it follows the rules. And the rules are up there with the definition. So, are the exponents whole numbers? Let's look. You can go back and forth. Yep, all the exponents are whole numbers. I got 3, I got 4, and I got 0. Okay. Next one. Are there any variables in the denominator? I did not see any variables in the denominator. Awesome. All the variables are in the numerator. Are there any variables in the exponent? And are the coefficients real? Let's see. Any variables in the exponent? Nope, my exponents were all 3, 4, or 0. And all my coefficients are real. So in fact, this is a polynomial function. So we'll say yes. If so, make sure it's in standard form. All right, so let's write it in standard form. I'll just put SF to let everybody know that I'm doing standard form. So your highest degree term should come first. So that's going to be f of x equals x to the 4th. And then my next degree term is going to be negative 0.8 x cubed. And then my constant, state the degree. So we know that the degree, I'll just use D for degree. Maybe I should give some kind of abbreviation. We'll make this T, and we'll make the leading coefficient, how about LC? So that way I know what I'm talking about. All right, so the degree for this one is going to be, well, highest degree is 4. Okay, I need the type. Well, it's to the 4th degree. So remember quarters, right? 4th degree is quartic. And the leading coefficient is the coefficient of the leading term, which is the term with the highest degree. I don't see a number there, so what is it? It's 1. Okay, A is done. All right, let's look at B. Well, what I notice here is that x is being raised to the negative 2 power. So if I were to simplify this, this would actually be 2x squared minus 1 over x squared. So it is not following the rule that states that there can be no variables in the denominator. So this is not a polynomial function, so we'll say no. So you don't have to do the rest of the problem. All right, let's look at C. Well, let's see here. We got a pi. That's weird. What is pi? Well, guess what? Pi might be irrational, but it's not imaginary. So pi is just approximately 3.14. Goes on forever. It is irrational, but that's okay. So let's see. Does it fit or match all the criteria of that definition? Exponents are whole numbers. There's no variables in the denominator, and there's no variables in the exponent, and coefficients all have to be real. I think we are meeting all of those. Even though that pi doesn't look like a number, it actually is. So we'll say yes to C. Put it in standard form. It already is. Let's just put it as. State the degree. The degree looks like it goes, the highest degree is the second power. The type, so if it's the second degree, then we know that it's quadratic. Hopefully you've got that one down. And what is our leading coefficient? Well, that's interesting. It's pi, right? So go ahead and write pi. All right, D. Well, notice that our variable is in our exponent. That is a exponential function. That is not allowed. That is no variables in the exponent, right? So this is no. This is not going to be a polynomial function. So example 2, nothing is new. You're going to use direct substitution to evaluate f of x. I didn't tell you what to evaluate it when, let's just write that over here, when x equals -5. Oops, my bad. All right, this should be pretty straightforward. We're basically just going to plug -5 in for x. And then we are going to evaluate it and simplify. All right, so -5 cubed, well, that's going to be negative. Well, -5 times -5 times -5 is negative, so it's -125. 3 times -5 squared, well, -5 squared is 25. 6 times -5 is -30, minus 11. Simplifying a little bit more. That's -41. And all together, this is going to end up giving us -91. Nothing new. You've been doing this for a really long time. All right, example 3. Now we're going to use this new thing called synthetic substitution to evaluate the same function as in example 2. And this is new to you, so take more notes than what I'm actually writing down. Okay, so what you're going to do is we are evaluating this when x is -5. So I am going to write a -5. And then I am going to do like an upside down long division sign. And I'm going to leave enough room for 2 rows. On the top row, I'm going to put all the coefficients of my polynomial. So coefficient of the first term is 1. Coefficient of that second term is 3. Coefficient of the third term is 6. And the constant is -11. Okay, here's where you're going to want to take a little extra note. So here's how this works. It's a procedure. Okay, you bring down the 1. Now you take that number, 1, and you multiply it by -5, and whatever you get, you put under the next coefficient. So 1 times -5 is -5. Add those together. You get -2. Take that -2, multiply it by -5 again. You get +10. Add. So you get 16. You see how we're like adding, multiplying, adding, multiplying. Okay, so write a little note off to the side for yourself so that you don't forget. And then multiply 16 times -5, you get -80. Look at what I just got. I just got the exact same thing as when I plugged in -5 into the polynomial function. And I actually think that synthetic substitution sometimes is easier. I don't have to break out a calculator. I don't have to raise things to the 3rd power. Okay, so sometimes it's easier. Sometimes it's easier to evaluate. Now, there is a relationship here. And synthetic substitution becomes really important when working with polynomial functions. It is kind of another way of factoring. And I'll explain way more about that later. Okay, super, super important. Now, I just did an easy synthetic substitution problem. My polynomial was already in standard form, but if it's not, you need to make sure to put your polynomial in standard form. Okay, so that's always the first thing you want to do. Also, if you're missing any terms, so our polynomial that we just worked with wasn't missing any terms. It went from a cubed to a squared, to a first power, to a constant, or x to the 0. Well, if it was missing terms, like for example this next one, I'll highlight that. So here's our next polynomial function, and once I put it into standard form, you will see that we are missing some terms, and I'll tell you that we are going to insert some zeros for those missing terms. All right, so let's start by writing this thing in standard form. So in standard form, leading term is going to be -x to the 5th. Now, I don't have an x. Well, let me go ahead and finish writing it in standard form. So my next term will be x squared, and then I'll have my constant. Now, notice I don't have x to the 4th, I don't have x to the 3rd, and I don't have x to the 1st power. So what I'm going to do is I'm going to insert zeros for any missing terms. Now, I wouldn't normally write it like this in standard form all over again. I'd go straight to synthetic substitution. But I'm going to spend the extra time right now just while you're learning this, showing you how I'm plugging in zeros for every missing term. So this would be like 0x to the fourth, which is still just 0. 0x to the third, which is still just 0. I've got my x squared. I don't have an x term, so plus 0x and then minus 3. Okay, so these are the zeros I'm going to need to insert for my missing terms. All right, synthetic division now. I put the -1 on the outside. Leave myself enough room for 2 rows. And then I put the coefficients of every single term. And any missing ones get a 0. So I've got a -1, 0, a 0, a 1, a 0, and a -3. Okay, time to do the procedure. You bring down a -1. Okay, -1 times -1 is +1. Add. So that gives you a 1. 1 times -1 is -1. 0 plus -1 is -1. -1 times -1 is 1. Add. 2. 2 times -1 is -2. Add. -2. -2 times -1 is going to give us +2, and we end up with a -1. So if I were to actually plug in -1 into f of x, I would know that it's just going to equal -1. And some of you may be saying, well, maybe I just plug -1 in. Awesome. You could also do that. There are going to be times when you're not going to want to, though. And there's other reasons, like I said before, why we would do this. But let's just double check that we got the right answer. -1 raised to the 5th power is going to be a -1, so this is just +1. And I end up with -1.